Chapter 8 Thunderstorms, Mid-Latitude Cyclones and Hurricanes. Section 8.5 Tropical Weather and Hurricanes. So tropical weather is dominated by two systems. Along the thermal equator, we have the intertropical convergence zone. At the intertropical convergence zone, we have the meeting of the trade winds, which creates this atmospheric convergence. And we also have convective processes occurring because this area is so warm. And both of these together lead to a development of many, many thunderstorms. If you were to look at a single location along the intertropical convergence zone, thunderstorm development is almost guaranteed every couple days. Outside of the intertropical convergence zone, and that zone stretches roughly about 5 to 10 degrees either side of the thermal equator, we get the subtropical high pressure zone. The subtropical high pressure zone is dominated by descending air that's the result of Hadley cell circulation. It's basically cloud free, and it's produces features like the Sahara Desert, the Kalahari Desert, the dryness of the Middle East, and generally dry zones over the Pacific and Atlantic and Indian Oceans. There are also seasonal oceanic disturbances in the trade winds that occur in late summer, early fall. And these disturbances can form thunderstorms, and if the thunderstorms organize, they can develop into tropical storms or hurricanes. So as I said, one of the most important weather features in the tropics is the intertropical convergence zone. It is a wide band of cumulus and cumulonimbus clouds that are created by atmospheric lifting. This lifting is a function of both convergence of the trade winds and heating causing convection. Weather disturbances in the trade winds known as easterly waves are another source of cloud development and precipitation in the tropics. And these tend to form over the oceans that have warm temperatures, over 26 degrees Celsius surface sea temperatures. And as I said, these disturbances are seasonal. They're late summer, early fall. It's important to recognize that the zones that I'm talking about, the intertropical convergence zone and the subtropical high pressure zone, they move back and forth depending upon the season. So for example, in the top part of this diagram, we see that the intertropical convergence zone moves south of the equator and occupies a region, roughly about 20 degrees south during the December solstice. During the two equinoxes, we would find the intertropical convergence zone at the equator. In the June solstice, this intertropical convergence zone moves north of the equator. And similar movements occur with the subtropical high pressure systems. So let's talk more about these easterly waves. They're essentially associated with the intertropical convergence zone. It's sort of late summer, early fall location. You can spot these easterly waves on a weather map. They appear as a bend in the isobars. And on the eastern side of the wave, convergence occurs, forming thunderstorms, divergence on the western side. If the convergence on the eastern side is strong enough, it can organize into a self-sustaining low-pressure system and may become a tropical storm or a hurricane over time. So here's a typical location of these easterly waves. This would be late summer, early fall. It's in the Atlantic Ocean, and this can generate an Atlantic hurricane during these months. So as I mentioned, another important feature is the subtropical high pressure zone. So this is primarily descending air that is the result of the Hadley cell circulation. It produces clear skies, low humidities, and very, very hot daytime temperatures. And of course, this subtropical high pressure zone migrates seasonally. It generally influences locations 10 to 23 degrees north and south during some part of the year. So here we see another diagram showing the intertropical convergence zone and the subtropical high pressure systems as they relate to the Hadley cell, and the sort of uplift that occurs at the intertropical convergence zone and descending air that occurs at the subtropical high pressure zone. So hurricanes are a nasty storm that form in the tropics. They're a cyclonic storm, so that means the air is moving inward and upward. And they only develop over warm oceans. Hurricanes do not develop over land. They need a lot of latent heat energy. They also go by various names. In Australia, they call them cyclones. We call them hurricanes. North Pacific typhoons, and in the Philippines, bagyo. These hurricanes have a very similar look to them. They consist of spiraling arms of thunderstorms that move into a cyclonic circulation system with an eye at the center, and at that eye, that's where you get the lowest pressure. They look very, very similar when you see them. Here are 4 different storms. As you can notice, that you can see this swirling arms. All of these are in the northern hemisphere. I can tell that because it's counterclockwise and inward. They would be clockwise and inward in the northern hemisphere. The surface pressure of a hurricane can become extremely low. The lowest pressure reading ever recorded for a hurricane was a typhoon tip. So this affected, it was a Pacific storm that affected somewhere along in Asia. In 1979, it had a pressure of 870 millibars. The average pressure of a hurricane is about 950. To be classified as a hurricane, the sustained winds of one of these storms needs to be greater than 118 kilometers per hour. And that usually occurs with an atmospheric pressure of about 980 millibars or lower. Wind speed in the hurricane is directly related to surface pressure of the storm, and this graph illustrates that. As you can see, as pressure, that each one of those diamonds represents a measurement at a storm, its atmospheric pressure, and associated wind speed. And you can see that there's a linear relationship. As pressure decreases, you get a linear change in the wind speed of the storm. Hurricanes are quite dissimilar from mid-latitude cyclones. They don't have fronts. They're not associated with the mixing of warm and cold air like mid-latitude cyclones, which occurs at the polar front. They are basically generated by just warm air that generates or develops over warm seas. And they consist of many organized thunderstorms. So there's hundreds of thunderstorms taking place in a hurricane over its lifespan. They are also much smaller than a mid-latitude cyclone, about half the size or a third of the size, with an average diameter of about 550 kilometers. And they usually have a cloud-free eye. And the eye becomes more prevalent as the storm is building in intensity. When the storm starts dying, the eye fills in. And the death of hurricanes, most hurricanes die from 2 reasons. Either they move on to land and lose the latent heat associated with evaporating seawater, or they move into cold ocean currents or ocean conditions. The strongest winds and heaviest precipitation are found in the area just adjacent to the eye, and the eye basically consists of a vertical wall of thunderstorm clouds that extend from the Earth's surface to the top of the troposphere. So as I said, hurricanes are powered by latent heat energy, and that's released from condensation. So warm air is lifted up into the storm, and it condenses, releasing a lot of heat energy, and that creates this cyclonic system. How warm do the oceans need to be? They need to be warmer than the surface of these oceans need to be warmer than 26.5 degrees Celsius, and there needs to be extensive depth of warm water, about 200 meters of warm water to supply the energy required to power a hurricane. As I said, hurricanes dissipate when either they hit land or they move into cooler seas. Most hurricanes live for about a week. They chug along. In the Atlantic, they'll form either in the Gulf of Mexico or out in the Atlantic and move towards the southeast coast of the United States. Hurricanes do not develop in the area 5 degrees either side of the equator. They require Coriolis acceleration to get that spinning motion. So here we see a cross section of a hurricane, and the red arrows show the warm air moving into the system, being then moving upward in individual thunderstorms. This warm air is developing because of high evaporation over this layer of warm ocean, warmer than 26.5 degrees Celsius. The air moves up into the thunderstorms. Thunderstorms produce heavy rains, and the outer edge at the top of these hurricanes usually consists of cirrus clouds. So not all ocean basins produce hurricanes. So the Pacific Ocean in the southern hemisphere and Atlantic Ocean in the southern hemisphere just doesn't get warm enough to form a hurricane. Hurricanes need the warm ocean waters, and probably the area of the world that produces most hurricanes is not the Atlantic, but the Western Pacific produces the most. This map shows some general directions that these hurricanes will move in the Atlantic Basin, Northwest Pacific Basin, and Northeast Pacific. And then we see in the Southern Hemisphere for the Pacific Ocean and the Indian Ocean. So here are some of the tracks of these storms superimposed on a map. So 1985 to 2005, these are the storms occurring in the Eastern Pacific, North Pacific, and in the Atlantic Ocean in the Northern Hemisphere. And each those lines represent the pattern or the track that they took. The color of the dots there represents the strength of the storm, and the storms have a hurricane has 5 categories: 1, 2, 3, 4, and 5, and with increasing strength. Here are the storm tracks for the other part of the world. So we're seeing the Northwest Pacific and the Indian Ocean and the Pacific Ocean, the Southwest Pacific Ocean, Southern Hemisphere, and the Southern Indian Ocean in the Southern Hemisphere. The number of hurricanes that occurs in the North Atlantic averages about 5.9, and that's based on data from about 1950 to about 2002. The Northeast Pacific, so that would be on the other side of Mexico, about 7.4 hurricanes per year, and there does seem to be a trend of an increasing number of them, but that may be related to the fact that we just didn't spot them because we didn't have satellite imagery prior to about mid-1965. As I said, the basin that produces the most hurricanes is the Northwest Pacific, an average of about 18 hurricanes per year. So when do they occur? These graphs show us the peak season for the North Atlantic Basin, the Northeast Pacific Basin, and the Northwest Pacific Basin. So September for the North Atlantic, looks like about August for the Northeast Pacific Basin, and once again August for the Northwest Pacific Basin. Of these three basins, the one that produces the most strong Category 3, 4s, and 5s is the Northwest Pacific Basin. Those Category 5 storms are generally rare in the Northeast Pacific Basin and in the North Atlantic Basin. So how does hurricane classification work? This table illustrates it. So they begin calling one of these storm systems a tropical depression. Tropical depressions have wind speeds of less than 64 kilometers per hour. It then, if the speed increases above 64, then it's a tropical storm up to about 118 kilometers per hour. Above 118 kilometers per hour, we have an official hurricane occurring. And there are 5 categories, the strongest being Category 5. Category 5 storm has sustained wind speeds near the eye of about 250 kilometers per hour. Notice that we've also got measurements of average storm surge associated with them because the winds are blowing inward. The ocean, the top of the ocean moves into the center of the storm and rises because of more water being poured on or pushed there, and also because of the low pressure lifts the surface of the ocean. And associated with the various categories, there's also information on the pressure. What is the atmospheric pressure range for Category 1, 2, 3, 4, and 5. So you can see 5, the pressure drops to below, and that's at the eye, below 920 millibars. As I said, the storms are fueled by warm seawaters. So in this picture here that we see, that we can see the temperature of the seawater, with red being the hottest, blue being the coldest. And this is an animation. I'm going to turn it on in just a second, and we can watch one of the most devastating storms in the last 2 decades, Hurricane Katrina. So Hurricane Katrina is going to develop just to the west of Florida. It's going to go over Florida and then move into the Gulf of Mexico, where it's going to pick up a lot of latent heat energy and then strike New Orleans. And you're going to see how strong the eye gets. The stronger the storm, the bigger the eye. So let's watch this animation. There we go. So there's the storm, crosses Florida, hits New Orleans, and then dissipates quickly as it moves over land. The Katrina hit New Orleans August 29th, 2005, caused extensive flooding. The number of deaths was estimated about 1,836 direct and indirect deaths. That particular season, 2005, had many hurricanes. In fact, they ran out of names. They usually named them from A to Z. They had to go and create new names after the storm with the name Z occurred. So beta and epsilon here. And you can see some of the major storms, how low their pressure got, and the amount of damage in US dollars. And that year was quite devastating. So you can see Katrina alone is estimated to have caused greater than $81 billion in damage. And there was several storms that were in the billion-dollar range. Dennis, Katrina, Rita, Stan, and Wilma. Here is a graph showing the storms when they formed, their wind speed over time. So we're moving from day 150 all the way to day 350 in December. And so that line represents when the storm started as a tropical disturbance, and then when it reached its peak, and then its dissipation. So the first one there is Arlene, and then we can see Brett, Cindy, Dennis, and Katrina wasn't the strongest storm that year. Rita and Wilma had much stronger winds. Now, how does that compare to other years? So, as I said, 2005 was a really bad year. The previous year, 2004, was more of a typical year, and there we can see the storms that formed that year. And notice the storm started a little bit later and basically stopped in October. Here is another year of data, 2017, which was a bad year. That's the year that Harvey occurred, and Irma and Maria. So this occurred in Trump's first year of presidency. Do you remember when he was tossing the paper towels out to people as relief for hurricane damage? And Hurricane Harvey caused extensive flooding to Houston. The storm stalled over Houston and dumped about 60 inches of rain, which would be, let me get this right, almost 2 meters. Here is satellite animation showing Hurricane Harvey, and we can see the slow-moving cloud, and it stalls over Houston, dumping a lot of rain. So now you can see the storm is at most intense, clear eye, large eye. And here's a picture of some of the flooding that occurred in Houston, Texas. So all the streets inundated, houses flooded, quite a bit of damage.